Now let's see. Let's do it from here. Let's do it. Should we do both? Well, let's run out the vote. I don't know if you guys are getting bored by me being pedantic. Should I do just the one or should I do both? Both. You guys are already chanted, so I don't need to take it. Right. So, you need enough time to write this down while I was procrastinating. So let's do method one. So I'm going to put them all in this method. I'm going to work out all inertias from that common point over there, about which I'm rotating the whole system.
Because of the shape, what is going on?
So I need to get the inertia of each rod. And I'm going to use the parallel translation of axis theorem to get that inertia. I'm going to do it for the first rod. Which one? We label them 1, 2, 3. Alright. What's the distance between here, where I know the inertia, and here, where I want the inertia? Anyone got a clue how to work that out? Theorem of Pythagoras, maybe? We know the distance to here. We know the distance to here. We know that that's 90 degrees. And that can get us that distance over there. The distance to here, this length, is 4 over 3L. The distance, no, wait. It's not 4 over 3L, that's the center of mass that I'm drawing. I'm confusing you guys. The center of mass of the whole system is only a third of the way in. But the point I want is a half the way in. Right, I want this point. And that's what? That's half L beyond 1L. So that's 3 over 2L. Make sense? Let me draw it on another picture. I don't have other points. I've got this guy living a distance L from this point that I'm rotating from. And I'm interested in the center of mass of this rod, which is halfway through the rod. I want to know where it lives. So I can draw another, I can continue this line downwards, right? And I can drop it perpendicular. When I do that, this is halfway along, right? So this length here is L over 2, which is halfway along this rod. Whereas this length here was L, that was given. So that side of the triangle, which I haven't drawn, that side of that triangle, that particular triangle, has got a length of 3L over 2. Right. This side of the triangle has got what length? L over 2. So now I can get the length of this side of the triangle using Pascal's theorem. It's going to be 3L over 2 squared plus L over 2 squared under the square root. Yeah, okay, so there's a minus in here. Right, so I'm only really interested in length, which always helps with quantities, but yes, I mean, it's minus if you've got some coordinates. Right, so that's D. In fact, let's not even bother square rooting D because we're going to need D squared, aren't we? We're going to need D squared when we use the parallel translation of axis theorem. So let's just work out D squared without square rooting anything. This is equal to 9 over 4 plus 1 over 4, which is 10 over 4 L squared. Right, that's D squared for the first rod. What's the distance to this one going to be? Exactly the same, exactly. And the distance to this one? Not the same. Very simple, this one. Oh, right? Yeah. So let's work out. I1 is going to be equal to ICM, which we know is 1/12 ml squared, plus m times d squared. Okay, so that's going to be equal to a fun thing to compute. 4 3s, 12, so 10 3s are 30, 31 12s, NL squared. And this is also going to be I3. Because we agreed that this distance was the same for I3 as well, or for the third rod. This rod and this rod have the same D. So I2 is the only one that's different. I2 is going to be, the distance now is L. So we're going to have 1/12 NL squared plus NL squared, which is simply going to be 13 NL squared. So now we've got all the three inertias computed around the exact same axis. Because they're all at the exact same axis, we can now add them up and get our total inertia. I'll come back and do method 2 after computing the kinetic energy because it doesn't make sense to do it before. Right here, the inertia total is going to be the sum of the inertias. It's going to be 31/12 times 2, that's 31/6. It doesn't really matter because we're going to be adding it to something over 12, so let's just make it 62 plus 13/12. And that is 75/12. So there's the inertia when rotated around that one point. The next question is most likely going to be the kinetic energy. What is the kinetic energy of the pendulum as a function of the generalized coordinate and its derivatives? Because we're on method 1, because the point about which we computed the kinetic energy is stationary, is fixed. The ceiling is not moving. I'm not allowing it to go up and down whilst rotating the pendulum. If I was, this would be rubbish. But it is fixed. It is not moving. So I can write the kinetic energy like that. One term. It's not a sum of two terms, it's one term. And that's method 1. I found a fixed point, I worked out all the inertia of the system around that fixed point, and then the kinetic energy can be written like this. If there was no fixed point, or if I for some reason did not feel like writing the inertia around that point there, then I would have only one other option. I would have to work out the inertia about the center of mass of the system. And then I would get two terms in the kinetic energy. We will do that in a minute. But I want to stress that. This point is fixed, it's not moving. And that's why we can write the kinetic energy like this. If that point was moving, we'd be out of business straight away. We have the kinetic energy. And that is obviously going to be equal to 75 over 24 and L squared into dot squared. I'm going to write it down in my little block of things that I don't erase. Right. Let's put this all to the test. Let's do method 2 and hope and pray that we will get the same answer. If we don't, some mistake has been made somewhere. When we do method 2, we are now going to compute all the inertia inertias of all the rods around the center of mass of the system, not around that point over there. At first shot, this looks a little bit more difficult than method 1, because in method 1, at least one of them was nice and easy. But in method 2, that's no longer the case. We now have a similar drawing. Mirror it exactly if I can. We're interested in getting these moments of inertia around that point. Over there. 1/3 of the way down. When we know it here, here, and here. Right, I suppose there is still one easy one. But the thing that we need a D for look at that triangle. And we need to know the lengths of the sides of that triangle. And what are they? This one is still L over 2. We know that the distance from here to here is L over 3, because when we compute the center of mass, we got an L over 3 from here to here. The question is, what is the distance from here to here? Well, we know that the total distance from here to here is L over 2. So from here to here must be the difference between those. It must be L over 2 minus L over 3, which I believe is L over 6. So, we have L over 6 on one side of our triangle, L over 2 on the other side of our triangle, and therefore the distance squared is going to be L over 2 squared plus L over 6 squared. Which is 40 L. What is this? Maybe we should just multiply that one by 9. That's much easier. So it's 10 L squared over 36, which is divide both sides by 2, 5 L squared over 18. Right. So that's the distance squared, and it's going to be the same again for that one. So d1 and 3 squared, and d2 squared, the distance to the second rod, is going to be just this distance squared, L over 3 squared, or L squared over 9. So, when we work out these things, we get the moment of inertia of the first one to the center of mass is 1 over 12 ml squared plus m times 5l squared over 18. 5 over 18 ml squared, which is equal to get them over 36 again. 12 3s are 36, 18 2s are 36, this would be 13.